The European CERN is the Center for Particle Research, revealing the specifics of a new particle today. Accelerating something 3 times, it is larger and twice as deep. Discovered, 3 brand new particles could assist us in understanding the universe's birth and what its future looks like. Scientists at CERN have just unveiled findings that alter our perception of the universe on its head. Beneath the surface of their revolutionary experiments lies a world of particles and strange forces that could be straight out of a sci-fi novel. From openings that could lead to other dimensions to particles that pose a threat to the very foundations of reality, what mysterious secrets are hidden within these experiments? Let's dive into the world of CERN and discover the information that may redefine our universe as the entry point for new dimensions. A wormhole might theoretically appear out of nowhere, and the reason would be the sky. And groundbreaking research carried out at the Large Hadron Collider, located at CERN, is underway. The Large Hadron Collider, LHC, also known as the most effective accelerator for particles, is located near Geneva, straddling the border between France and Switzerland. There are secrets about this strange organization that the world has no knowledge of, secrets that may change how we view physics and everything regarding the European Organization for Nuclear Research. This massive instrument for science stretches for 27 kilometers and is deep beneath the surface. The primary purpose of the Large Hadron Collider is to allow physicists to test the claims made about different theories of particle physics. This includes the well-known examination of the conventional model of particle physics that aids us in comprehending the fundamental structure and the universe's fundamental blocks. The Large Hadron Collider works by accelerating protons to nearly the speed of light before smashing them together. These collisions produce a shower of new particles that researchers study to gain insights into nature's laws. It was through such experiments as the Higgs boson, referred to as the God particle, that was found in 2012. This discovery helped confirm how particles gain mass and played a significant role in particle physics. The experiments carried out at the Large Hadron Collider are necessary for comprehending the phenomena that take place under extreme conditions, similar to those just after the Big Bang. The accumulation of data following the Big Bang can provide additional information about how the universe began, progressed, and about the fundamental constituents of matter. The Large Hadron Collider plays a role in potentially revealing new aspects of the real world that could help solve mysteries surrounding dark matter and the fundamental forces of nature. However, CERN's advanced experimentation does not come without concerns. Some speculate about the creation of high-energy experiments, strange objects, or black holes that could arise. Despite the fact that CERN ensures all safety precautions have been taken and that the scientific community closely monitors these studies, theoretical models demonstrate that risky scenarios are extremely unlikely. Through its ongoing research, CERN's discoveries help us better understand the universe and demonstrate the amazing capacity for human ingenuity and collaboration in the pursuit of knowledge. Unveiling the LHC. Humanity's modern marvel, the Large Hadron Collider at CERN, is not merely an impressive piece of technology. It is a marvel of modern science and engineering. Situated beneath the French-Swiss border, a large collider traverses a tunnel 27 kilometers in circumference and up to 175 m in depth. Because of this, it is the largest underground particle collider in the world, one of the most significant instruments in the field of particle physics. The structure of the Large Hadron Collider is designed to handle experiments of unprecedented scale. The main ring of the collider, housed in a tunnel with a diameter of 3.8 meters, contains 2 adjacent parallel beam pipes that direct protons in opposite directions. These protons are accelerated by a series of superconducting magnets, which are essential for preserving the path of the protons, adjusting their course at speeds close to the speed of light. The beam pipes are surrounded by layers of cooling systems that maintain a temperature colder than space, necessary for maintaining the superconductivity of the magnets and ensuring they work as they should. The Large Hadron Collider is further highlighted by the thousands of magnets it uses, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to direct their attention. The biggest and strongest are 15-meter-long superconducting magnets, weighing 35 tons each, showcasing the vast physical dimension and technological ambition behind the Large Hadron Collider. The primary goal of the Large Hadron Collider is to explore the fundamentals of the universe by observing the smallest components of matter. By causing particles to accelerate to nearly the speed of light and then collide, the Large Hadron Collider allows physicists to study the resulting particles produced during these collisions. This method aids in testing and enhancing our comprehension of the standard particle physics model, which is currently the most accurate description of the subatomic world. One of the key objectives behind the Large Hadron Collider's experiments is to explore the mysteries of the Higgs boson. Its discovery in 2012 at CERN established theories about how particles gain mass. The Large Hadron Collider also investigates other fundamental particles and forces, aiming to address critical questions such as the existence of dark matter and the nature of the universe and matter shortly after the Big Bang. Furthermore, the Large Hadron Collider seeks to verify the presence of new particles predicted by theoretical physics but not yet observed. These experiments are necessary for possibly discovering new physics beyond the Standard Model, including supersymmetry and dimensions beyond the familiar three spatial dimensions. The larger-than-life vision of the Hadron Collider is more than just to understand the universe's building blocks but also to foster international collaboration, with thousands of scientists from more than 100 nations working together. The Large Hadron Collider is evidence of international cooperation in the quest for knowledge. The structure, as well as the size of the Large Hadron Collider, allow it to deal with some of the most serious physics questions, and its purpose extends beyond mere scientific curiosity, aiming to deepen our understanding of the universe and inspire worldwide collaboration in science. Through this enormous and intricate apparatus, humanity keeps pushing the boundaries of what is known and the journey ahead. How does the Large Hadron Collider really work? At the heart of CERN's research facilities, the Large Hadron Collider is a powerful tool for examining the quantum realm, allowing scientists to observe and study the fundamental particles that make up everything in the universe. The process of particle acceleration and collision at the Large Hadron Collider is a key method for probing the foundations of physics. Inside the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel inside ultra-high-speed tubes under high vacuum, mimicking the conditions of outer space. Superconducting electromagnets, chilled to temperatures. Discovery of the quark-gluon plasma, a state of matter that existed just moments after the Big Bang. This discovery, which occurred in 2015, allowed scientists to understand the behavior of matter under extreme conditions, offering a window into the early universe's first moments. By recreating the conditions of the early universe, the LHC gives us a deeper understanding of how the building blocks of matter came together to form the cosmos we see today. Another critical area of research at the LHC is dark matter, a mysterious substance that accounts for about 27% of the universe's mass, yet cannot be directly observed. Scientists believe that dark matter interacts with regular matter through gravity, but not through electromagnetic forces, which is why it is invisible to telescopes and other instruments. The LHC experiments hope to detect potential dark matter particles by studying the interactions between ordinary matter and potential dark matter candidates, such as weakly interacting massive particles, WIMPs. Additionally, the LHC is investigating extra dimensions. String theory predicts the existence of dimensions beyond the familiar three spatial dimensions and time, potentially offering new insights into the nature of the universe. The search for evidence of extra dimensions is one of the most exciting frontiers in physics, and experiments at the LHC are providing crucial data that could point toward the existence of such dimensions. The LHC also plays a key role in exploring the fundamental forces of nature. In addition to the gravitational and electromagnetic forces, which we experience daily, there are two other fundamental forces that are important on the subatomic level: the strong nuclear force and the weak nuclear force. The LHC's experiments probe how these forces govern the interactions between particles, helping scientists to refine and possibly extend the Standard Model of particle physics, the theory that explains how the fundamental forces and particles interact. Beyond these scientific milestones, the LHC has also contributed significantly to technological advancements. The need for precise and reliable measurements in particle physics has driven innovations in computer technology, including the development of the World Wide Web, which was originally invented by Tim Berners-Lee at CERN to facilitate data sharing among researchers. Additionally, the LHC's complex systems require cutting-edge advancements in magnet technology, superconducting materials, and data processing techniques, all of which have broader applications in fields ranging from medicine to aerospace. The collaborative nature of CERN's research also fosters international cooperation, bringing together scientists, engineers, and researchers from all over the world to work towards a common goal: understanding the fundamental nature of reality itself. With over 10,000 scientists and engineers from more than 100 countries contributing to the LHC's work, CERN exemplifies how global collaboration can lead to groundbreaking discoveries that push the boundaries of human knowledge. In conclusion, the Large Hadron Collider represents one of the most ambitious scientific endeavors in history. Its experiments have already led to remarkable discoveries, and its continued research promises to unlock even more profound secrets about the universe. As humanity strives to understand the very building blocks of reality, the LHC stands as a testament to our collective curiosity, ingenuity, and determination to explore the unknown. Through its research, the LHC is not only revolutionizing our understanding of the universe but also paving the way for future breakthroughs that could reshape our world. The existence of pentorks has confirmed the discovery of tetraquark particles consisting of 5 and 4 quarks, respectively, which had not been observed before. These discoveries enhance our comprehension of hadronic matter, which is made of quarks united by the powerful force that holds the atom's nuclei together. These findings show the predictive power of the Standard Model and also open up brand new research horizons, providing insights into particle physics and the behavior of matter under extreme conditions comparable to the ones that followed the Big Bang. Science is put in danger by the Big Bang Theory, or science fiction, as the capabilities of the Large Hadron Collider's expansion have been so. Due to the hypotheses regarding its potential risks, two of the most talked about theoretical dangers associated with the Large Hadron Collider include stranglets and the capacity to reproduce micro-black holes. These scenarios have captured public interest and scientific observation. Strangelets are a more theoretical form of matter, more stable than ordinary matter. The hypothesis states that strangelets could transform anything they encounter into strange matter. The concern associated with this theory is if strangelets occurred during collisions of particles at the Large Hadron Collider, they could possibly start a devastating chain reaction, transforming everything that exists on Earth into strange matter. However, extensive research and safety evaluations carried out by CERN and the global scientific community have addressed these concerns. Studies have shown that if strangelets could indeed exist and were created on a massive scale at the Hadron Collider, they would probably be extremely unstable, and they would degrade too quickly to cause any changes to Earth's matter. In addition to this, high-energy cosmic rays, which come from space, frequently strike the Earth with energies much higher than those produced by the Large Hadron Collider, which did not produce any strange results. From this natural experiment, it is clear that strangelets are not a credible threat. The idea that the Large Hadron Collider, LHC, could create micro-black holes is based on theories of additional dimensions in physics, as described by some theoretical models. The LHC's energy collisions might produce tiny black holes that would evaporate quickly as a result of a process known as Hawking radiation. Experts in the wake of physicist Stephen Hawking concur that if tiny black holes were ever made at the LHC, they would occupy no prior threat. No such black holes would be incredibly small and quick to evaporate before they could interact with surrounding matter. Secondly, the LHC's energy requirements, although immense by human standards, are still significantly lower than the collisions of cosmic rays that occur naturally. Since no harmful black holes have been observed from interactions between cosmic rays, it is unlikely that any would be produced by the LHC. Rigorous safety checks are carried out by CERN and independent committees to make sure there is no danger posed by LHC-based experiments. These theoretical investigations are included in reviews and guidelines for safety and experimental data to address any potential risks. While the LHC's experiments keep pushing the boundaries of our understanding of physics, they are carried out with a high level of responsibility and scientific oversight, which guarantees that humankind can benefit from groundbreaking discoveries without taking unnecessary risks. Theoretical dangers often sound more like science fiction than real results from science. The scientific agreement, based on comprehensive research and natural cosmic events, is that the Large Hadron Collider is secure and that its potential risks are minimal. One of the most intriguing and unconventional experiments proposed is the investigation of magnetic monopoles. A monopole with a magnetic field is a hypothetical particle that is a magnet with a single magnetic pole, such as a north pole or a south pole. In contrast, typical magnets always possess both. The existence of a north and south pole was predicted by Paul Dirac, a physicist, in 1931, who demonstrated that their existence would explain why electric charge is quantized, implying that it is only available in discrete amounts. Despite their theoretical importance, magnetic monopoles have never been observed at the Large Hadron Collider. Researchers at the collider have been looking for evidence of these elusive particles. If found, magnetic monopoles would revolutionize our understanding of magnetic fields and could lead to significant technological advancements, including the development of new forms of energy storage and transmission. Likewise, the discovery of magnetic monopoles would provide experimental evidence for overarching theories of string theory that attempt to explain all fundamental natural forces within a single framework. While the search for magnetic monopoles may appear mysterious, It exemplifies the spirit of exploration and curiosity that drives scientific inquiry at CERN. The quest for such rare and potentially revolutionary particles demonstrates the dedication of the Institute to exploring the uncharted and broadening the frontiers of human knowledge. Another unusual experiment at the Large Hadron Collider involves investigating the conceivable existence of particles that could travel at a speed greater than light, according to Einstein's theory of relativity. The speed of light is the ultimate speed limit in the universe. However, there are some theoretical models that suggest that particles called tachyons could exist that would always move more quickly than light. Detecting tachyons would fundamentally question our comprehension of spacetime and causality. While most physicists are skeptical about the existence of tachyons, the attempt to locate such particles at the Large Hadron Collider is evidence of the facility's willingness to explore even the wildest speculations about physics. The Large Hadron Collider also enables scientists to carry out experiments that imitate the conditions of the early universe immediately following the Big Bang. These high-energy collisions produce the state of matter referred to as quark-gluon plasma, which existed just a few microseconds after the Big Bang. By studying this plasma, physicists hope to better understand how the universe evolved from its initial high-energy state into the complex and structured cosmos we observe today. Fundamentally, these novel experiments at CERN, ranging from searching for magnetic monopoles to creating quark-gluon plasma, highlight the depth and ambition of the scientific research being carried out at the Large Hadron Collider. They demonstrate the push that CERN is making to break the boundaries of what we know about the universe and learning about new areas of physics that were previously considered solely theoretical. Conclusions and outro. The Large Hadron Collider's ultimate purpose is to push the boundaries of human knowledge, unlocking the universe's mysteries by colliding particles at unprecedented energies. It allows scientists to explore matter's fundamental nature and the forces that control the universe. This constant effort to comprehend the unknown reflects humanity's innate thirst for knowledge and exploration. The findings made at the Large Hadron Collider have far-reaching implications for our understanding of the universe. By examining the smallest components of matter and the fundamental forces at play,